Okay. Hello, everybody. My name is Aniket Kate, and today I'm going to talk about building multi-party computation applications securely on the blockchain. So, although I might be starting on a different note for where the previous talk ended, talking about FHE, but generally even FHE itself can be considered as one of the multi-party computation, one way to do multi-party computation. So I hope that by the end of my talk, you will find some synchrony, as well as I'm hoping to provide some comparison between multiple approaches which are available, which can solve all the problems in one case, but there will be trade-offs and other things to consider. I work at Supra, where we are building all sort of different oracles and randomness solutions, as well as MPC is certainly something we find as a very important role to play, building all sort of D apps in the future in general. So let me start with the first premise when we call as multi-party computation or threshold cryptography. I'll be focusing on what the setting which is called as honest majority, where I want to make sure that the computation finishes. So from the previous talk, when he mentioned that you required t is equal to n divided by 3, otherwise things will not complete. Here we'll assume I'm going to work in a even less stricter setting, which we call as honest majority. That means that as long as you have 51% honest parties or parties which are functioning, you will continue to have things working for you. But after that, it will not work for you. And this is also the term that is employed is called robustness to the environment or the guaranteed output delivery. Okay, so in such a setting, typically most of the cryptographic protocol, I'm using word most carefully, were built assuming something known as broadcast channel. So you have access to some channel where you post your text or messages, and you build your protocol on top of that in general. And if you assume that the network is synchronous, that means the messages reach from their source to destination in a predefined time period of delta that is defined already and cannot be broken, then we can build such broadcast channels. Okay, it's certainly something which is possible. However, it's really a meaningful question to ask if can we really consider when we build something on internet, if internet can be considered synchronous enough to build the broadcast channel. And here I'm just going to make first of the controversial statement from my talk is that generally, I don't know where to click it. Okay. So if we assume, so based on, if you look at all the networking research, uh, if we assume that the latency per round, and if we expect that to be at the millisecond level or in second level, we cannot assume internet to be a synchronous system. That's the reason when we look at today's Ethereum and Bitcoin, all the security analysts, they want synchronous network because they are much slower. But all the third generation blockchains, what we can call them, they all building protocols without assuming synchrony, which is a very meaningful thing to do. So if you want performance, if you want low latency, we cannot assume internet to be synchronous. And as it turns out, in that setting, what are the models? How to define it? There are two well-defined models in that space. One is known as asynchrony, which means that no bound is known, but we know that if a sender sends a message, it will reach the recipient sometime, maybe today, maybe even tomorrow, maybe in a millisecond, or maybe it may take several hours, right? But they will reach. There are no bounds known, and there is another well-defined or well-understood model which we'll call as partial synchrony, uh, where you say that okay, the time bounds are limited, but there can be events which are known as GSTs. So sometime network can become slow, but it will eventually come back and start to behave synchronously with a known bound delta. And both these models are built, solutions are getting built in this space in general. And as it turns out, this broadcast channel thing I mentioned, I'm not going will go through all the properties here because I want to use my 20 minutes for possibly having some questions in the end. But uh, but believe me that we can't build or can't even achieve these properties if you go for these broadcast channel properties in asynchronous network or in partial synchronous network. The key culprit is the termination, that everybody should terminate, and that just cannot be achieved using such broadcast channel model. Okay, so that's fine, right? So we don't want to solve our problems within synchrony. If you want to go beyond synchrony, start building protocol in asynchronous or in partial synchronous network, again where understood problem where there are some solutions present over there. But the key thing is that now you are making further assumption that you require more honest parties. So in your system you require now 67% honest parties for this to work. Okay, which could be fine, but maybe if you can do without it, that will be even better, right? And there is also one more issue that moment you do this asynchronous protocol or partial synchronous protocol, you have to build common coins, or you have to deal timeouts or view change and everything. So basically, the simpler, very informal way to look at it is that think that you want to build a new consensus, and on top of that, now you have to make it more privacy preserving. So it's task of that kind where it becomes equivalent to solving consensus, maybe multiply with twice in general. So that's a problem with the asynchronous MPC or MPC solutions in that space. There is obviously enters the blockchain, and there is already some thought process in academic literature which looked at trying to build MPC protocols using blockchain. So that can we use blockchain for MPC purpose? And answer is yes, but as it turns out, many of these solutions just treat that treat that blockchain just purely as a broadcast channel again. And the no surprises. Obviously, we build all these SMRs or blockchains assuming partial synchrony, asynchrony. So again, they do not satisfy these broadcast channel guarantees, right? So here is we can just focus on the informal characteristics. So on blockchains, we know that when I submit a transaction, it is sitting in the pool and it will eventually get added. But it may not get added in the next block. It may take one block or two block, or if it is events like CryptoKitties or all other interesting events, it can take even longer time. So we can only say that they will appear eventually, but can't give any timing guarantee, right? The other thing is that different receivers may see them in different time. It can happen that I only currently see block number 100 while we may see block number 102. So he might see a bigger view than me, and that's the reason my view at even this point of time could be different from others. Or but what property the blockchains can always provide is that like he will know that when I see block number 102, I'm going to see exact same information. So we have this what is known as prefix ordering, which is always present. So we are going to see information in exact same order, and that is available. I'm going to use at times maybe another term which we call blockchains. Maybe in more academic terms could be called as what is known as state machine replication or SMR. So at times whenever you see the term SMR, just believe me, I mean blockchain in case I did not specify that. All right. So given such blockchain model, indeed this broadcast channel property again cannot be achieved conceptually. Again, the culprit is the termination because we cannot differentiate between a party which did not send the message to blockchain or party whose message is just sitting in the mempool for a long time. And that's the reason we cannot differentiate and we cannot achieve this broadcast channel again. Okay, maybe at the minute level, maybe at the hour level, but we want to build protocol which work at the second and microsecond level, right? So what can we do? So thesis for my talk is, now that we build up this background, is that we can still build all these protocols securely, all these MPC protocols securely using blockchain, but we might have to make some small modification, but at times we may not even need to make modification. It's just that we have to think about them in a correct manner, and that's what we'll try to do. So my aim will be blockchain assisted protocol design towards it. So what I want to do with that is that I want to make just do the cryptography for all your MPC part. Rest all the network issues are taken care by blockchain. So that's the simple way to look at this, and that's why we can scale quite a lot, because for last 15 years we're building really good blockchains. Let's use them and build this cryptographic protocol very efficiently. Some things will not work and something not, and my job will be to determine what works and what doesn't work, and if something doesn't work, prove that this is a lower bound and I can't do anything about it. So let me start with the simplest of the primitive, verifiable secret sharing. So again, linking to the previous talk we got Shamir's secret sharing. In verifiable secret sharing, even the dealer can be malicious and may try to just have issues with that. And again, a very well understood primitive. We know that with broadcast channel, verifiable secret sharing is possible for even only for 51% honest parties are required, and we can build these solutions with unconditional privacy property. And the moment we go to the asynchronous model, again, we require much higher number of honest parties, 61% in general. Now, my aim is to actually build of such a VRF using blockchain, and I'm just showing there are more efficient way to do that, but I'm just showing the simplest of the thing. So there is a concept in verifiable secret sharing which is known as non-interactive verifiable secret sharing, which means that the secret sharing party is going to actually just send the information in as a one-shot message, and that one-shot message is completely verifiable, And indeed I want to publicly verifiable as well, so that anybody can look at this message and say that this secret sharing is correctly done and correctly performed. So the idea typically is that it will be an encryption vector for all the shares and a NISIC proof next to that, a non-interactive zero knowledge proof, proving that everything is done correctly. You just post that to SMR. It's a purely asynchronous process, and when anytime this node 2 or 3 anybody sees this information, they are going to see that exactly in that same order, so they can make the exact same decision. So there's no equivocation. If that even that node is Byzantine, and if let's say it's sent two messages, such messages, it doesn't affect, because node 2 and 3 is going to see them in exact same order, so they know that we always going to drop the second message and pick the first. So that's a prefix property that can be used, okay, in general. So we can build such a thing in general. So what it can allow us to now, if we have a reliable broadcast or SMR protocol available, we can use that to build VSS, which is a core primitive. Uh, by VSS, I mean verifiable secret sharing. There is a Shamir obviously there. But the interesting thing to observe for this, I can is that I cannot achieve unconditional hiding property. So that means I rely on the cryptography and encryption assumption for my hiding property. And that's a very interesting thing we observe. If you want unconditional hiding, even when you have SMR or blockchain available, you still require dishonest two-third majority in general. So something interesting to observe. Now let's start building next set of primitive. The next thing I will build after VSS will be distributed key generation, or DKG, which is, that means I want to build a threshold signing or encryption mechanism. The core primitive, there is a DKG, so that the secret share is secret share, but it's random and unknown, and no individual party knows that value. And what can be simple way to build such a protocol on blockchain? It just, yeah, have these NISIC, which non-interactive VSS I shared. Just tell them to send them all to the blockchain, okay? And we'll wait for the first T+1. And as you can see, because of prefix property that's always available, because of the ordering of the blockchain, we'll have exact same T+1 parties that everybody is going to pick. So we have exact same DKG that's available to here, because the agreement on common subset problem, for those who know the exact definition for that, comes free with the state machine replication or with the blockchain. So that's the reason. The important thing to understand, I'm not making no assumption about these links. Any of those links can be so. So my node 3 is always a slow node. Still my protocol continue to function correctly and precisely correctly in such an environment, right? So in general, again, same example, DKG, if you their protocol to build that in asynchronous fashion or in partial synchronous fashion, again require two-third honest majority or 67% honest parties, but with SMR case, we can do much better job. And that can allow us to have better resilience or better scalability. Both these things are possible in such an environment. So moving on to now, the next thing to do that will be to build the entire threshold cryptographic schemes, including MPC, in such an environment, right? So the first thing could be to how to build verifiable random functions, or threshold BLS signature, which are one of the easiest primitives. Once you got DKG, all these things can be built in purely asynchronous fashion with the point-to-point links, just assuming that. Again, only working with 51% honest party. We do not require honest majority in general. The next thing will be, let's say I want to do threshold ECDSA or EdDSA. Now we'll require something more complex, because here we'll require some kind of a multi-party computation working out for this environment. And then that means we have to talk about how to build. So we already manage additions freely. That's what DKG was. But for multiplication, we'll require protocol. And now what protocol can work in such an environment? Again, I don't want to go to two-third honest majority. I want to always remain in my 50% case. And the approaches that can work is one of the common approaches, which is a CDM approach in the literature, which employs threshold linear homomorphic encryption approaches and build a solution on top of that, such that now I can do multiplications and additions for such environment, which can be useful for ECDSA and EdDSA in general. So let's dig deeper a little bit into now what I mean by that, right? So on purpose, I made that linear part highlighted that, because that's where the difference between something like FHE, fully homomorphic encryption, and what we're discussing come in picture. So here we are assuming this additive homomorphic or linear homomorphic. That means you can add things on encrypted data, but you cannot multiply. Okay, what will you have to do for that is either you have to do some interaction, and I'm really hope to spend maybe at least 2-3 minutes to really provide comparison and trade-off from experiments and analysis that we can perform. So example for that is indeed barrier encryption. We heard about it. Class group encryption is also one more thing. We pick class group because we generally work on ZP, and that is it's turned out to be very good, and there are better and better libraries which are available for that. So it also because we also want fully malicious security, so zero knowledge proofs also become easier for class group. I don't need to go to range proof. I can just work on sigma protocols in general. So that's the reason we went for class group in general, but other things can also work conceptually in general. Okay, so the idea here is that you will have your messages encrypted, because it's addition, you can take messages and multiply and add them. So encryption indeed works out, and linear operations also work out. But for multiplication, you have to do more complex things. So sorry for some confusion there. It just like continue to read it as it is. There's some formatting issue probably with the PPT and things. But then this is well-known protocol, and there are improved and better versions of this, which are also possible in general. So basically, we can perform this multiplication, but the key difference here is that to perform this operation, the parties will have to post some message on the blockchain. Okay, it's not that it's just going to happen computation on the fly on the internet. Okay, for sure that's a trade-off on the negative side, but on what can we say about on the positive side? The positive side, then we can certainly say that the computations here can be cheaper because now we are working on more efficient data structures in general. So here is a comparison, possibly the most controversial slide I could think of, because there are just so many nuances here. But this is just my take so far and my understanding of that. So actually, I want to start with the top, even without going. So the way I look at it is, let's look at the bottleneck part. Right? So for FHE perspective, I'll say the key thing you have to deal with is the computation part, where it can be expensive. While if you look at MPC, with secret sharing MPC approaches, I will say the key bottleneck is as the number of parties go, my interactions is growing. And I need to perform more. This party has to publish this message, and I have to verify. If I want malicious security, I want to verify more and more information in this environment. So, but on the other hand, so let's take an example. Let's say it depends on what kind of computation we want to perform. If I'm going to decrypt very far regularly, that I'm not going to have too much data encrypted for long, I'm going to decrypt data regularly and encrypt, then I'll go for secret sharing based approaches, because decryption is the expensive part in this environment. And additions, operations can be faster. Multiplication will depend upon how's my network speed and my operations. If I have lots of multiplications, and let's say I'm doing A multiply with B multiply with C multiply with D, so on, then actually FHE can do a much better job as compared to, because the interaction is less, because otherwise I'll be doing at least log n number of interactions in the MPC approach. So knowing where we want to build these things, we can build interesting solutions. The key thing I want to add is malicious security, where you, even if you don't assume even for FHE that the guy who do secret sharing for the threshold decryption is not, it can be also tolerated and it can be also malicious, their problem do become much more harder. And that's the difference between Shamir secret sharing and verifiable secret sharing, just for the comparison purposes. So yeah, what's the conclusion? We want to build MPC protocol. Let's build them on the assuming that we have blockchain available. We can solve many interesting things, and we don't need to reinvent the wheel. Blockchains will solve all our networking problems. Let's just focus on the cryptography and solve those problems. It can allow us to provide solution which work for also higher threshold of malicious parties, which is always better. And those who are oriented, these are a couple of interesting open problems, like how to prove if you want unconditional hiding, then you required higher number of honest parties. What kind of encryption that we can employ, how to avoid encryption and ZK to some level are all interesting problems that I'm excited to see here. Okay, thank you.
I think we have time for one quick question. All right, I have a question. So is it 51% because you're assuming proof of work blockchain?
So these are concept, all protocols are purely asynchronous. So there is no, we,
We do like a BFT blockchain is 60, like 2/3, right? Not
yeah,
not 51%.
very good question. So that's the reason I'll assume that blockchain is already solved. And once you solve that, all other AC problem can be solved asynchronously, but still for 51%.
But only like so if you assume BFT protocols,
Yeah.
you don't get 51%, right? Well,
If
we'll bring this offline maybe.
Oh no, I mean, but I'll say that blockchain is already available by other means, and we have this is a different computing party we are trying to solve it.
Okay, got it,
Yeah,
got it,
yeah,
got it. Okay.
yeah.
All right.
But there is a one more angle I'll be happy to talk in person later.
Okay.
Yeah.
We'll bring it offline.
Thank you.
Cool.